So good morning, doctor and everyone. My name is Kehui and my metric number is 2186540. So today I will present my topic, visible light communication-based emergency alert system using LED streetlight. So this presentation is divided into three main parts. First, I will introduce a background and the basic idea of visible light communication. Then I will explain the technical circuit and system diagrams, including the transmitter, channel, receiver, MATLAB simulations, and prototype. And finally, I will discuss the impact of these systems on me, the community, and the country. So first, let me introduce the problem background. So during disasters or emergency situations, normal communication networks may become congested, unstable, or unavailable. For example, many people may try to make calls, send messages, or search for emergency information at the same time. So this can delay important warnings. At the same time, LED streetlights are already installed along the roads and in many public areas. So this means we may not need to build a complete new infrastructures from zero. So the opportunity is to reuse these existing LED streetlights as an additional local warning channel during emergencies. So the main point of this slide is that emergency communication needs reliability, and existing light infrastructures can be used more effectively. So now, this slide shows the overall workflow of my proposed emergency alert systems. First, the emergency control center selected a warning message, such as road closed. Then, this message is converted into a predefined AB code. In these examples, the code is 10110101. So after that, the LED streetlight transmitted this binary code using on and off light pulses. So the visible light travels through the channel and reaches the photodiode receiver. And the receiver detects the light signal, recovers the binary code, and finally displays the warning message or activates a button. So the complete workflow is road close to the 10110101 to the LED pulses and to the photodiode receiver, and then back to the road closer. So this slide gives a full system idea before going into the technical circuit. So this slide explains the transmitter parts. So the transmitter starts from the emergency message, and the microcontroller stores and generates the corresponding AB emergency codes. Then the code is converted into an OOK control signal. So when the bit is 1, the control signal turns on the MOSFET, and the LED streetlights emits lights. So when the bit is 0, the MOSFET turns off and no modulated optic pulse is transmitted during that bit interval. So the MOSFET is used because a microcontroller pin cannot directly drive a high-power LED streetlight. So the MOSFET works as an electronic switch, allowing a low-power control signal to control a high-power LED load. So in simple words, the bit 1 means the MOSFET is on and LED is on. So bit 0 means the MOSFET is off, so the LED is off. So this is how a transmitter converts binary data into optic pulses. So after the LED transmits optic pulses, the light travels through the visible light channel. So in this channel, the signal can be affected by several factors. The first factor is this distance. So when the receiver is farther away from the LED, the received light intensity becomes weaker. The second factor is the line of sight alignment. So if the LED and receiver are not well aligned, so the less light reaches the photodiode. And the third factor is the ambient light. So sunlight or other artificial lights can add background interference. And the fourth factor is the received noise, so which come from the electronic components in the receiving circuit. And the simplified mode is here. So XT is the transmitted OOK signal, and H is the channel gain, which depends on distance and alignment. So I ambient represents ambient light, and NT represents noise. So the key idea is that a stronger optic channel gives the clear signal, while a weaker channel may cause bit errors. So this slide explains how receiver work. So first, the modulated light reaches the photodiode. The photodiode converts the light signal into a small electrical current. And because the current is weak, so a transimpedance amplifier is used to convert it into a voltage signal. So when the signal passes through a filter or signal conditioning stage to reduce noise or unwanted fluctuations. So after that, a threshold detector decides whether each received bit is 1 or 0. So the decision rule is, if the received level is higher than or equal to the threshold, it is detected as bit 1. So if the received level is lower than the threshold, it is detected as bit 0. And finally, a recovered A-bit code is compared with the emergency code table. For example, 1011, 0101 to the row closed. So the receiver changes the optical signal back into a useful emergency alert. And next, I developed a MATLAB simulations to demonstrate a complete VLC link. So in these simulations, the users can select the emergency message and adjust 3 important parameters: distance, ambient light, and light of sight alignment. So the top part of the interface shows the visible light link from the LED streetlight to the photodiode receiver. And the lower left graph compares the transmitted emergency codes and the recovered codes. And the lower right graph shows the photodiode receiver signal, including the decision threshold and the ambient light baseline. So the simulations also calculate the optical channel gain, bit error rate, and link conditions. So this is a simplified link level simulations. So its purpose is to show how the system works and how channel conditions affect the received result. So this slide shows the simulation result under normal link conditions, and the selected message is row closed. So distance is 8 meters and ambient line is 25%, and the line of light alignment is 90%. So under these conditions, the oblique channel gains is 0.538. So the transmitted code is 1011, 0101, and the recovered code is also 1011, 0101. So the bit error rate is 0, and the link conditions not recovered. So this means the received optical signal is strong enough, and the threshold detector can correctly distinguish between binary 1 and binary 0. So under normal link conditions, the emergency alert can be recovered correctly. So this slide shows the result under poor link conditions. So the message is still row closed, but the distance is increased to 7.5 meters, and ambient light is 50%, and the light of sight alignment is 80%. So in this case, the oblique channel gain drops to 0.102, and transmitted code is still 1011, 0101. However, recovered code becomes incorrect. So the simulation shows 4 bit errors out of 16 bit. So it gives a bit error rate of 0.25. So as a result, the system shows link failure. And this happens because the received light signal becomes weaker and noisier, and some bit levels cannot be correctly detected by the threshold detector. So this result shows that VLC performance strongly depends on distance, ambient light, and alignment. And now I will show a short video of MATLAB simulations. Okay, so this demonstration helped visualize the full process from message selections to alert recover. And besides the simulations, I also built a simple prototype to demonstrate the physical principle. The prototype uses an Arduino Uno low-power laser module and light sensor module and the traffic light module. So in the prototype video, I test three conditions: clear line of sight, partial blockage, and complete blockage. Okay, so this prototype does not represent the full practical VOC system, but it clearly demonstrates OOK optical transmission, licensing, and link statute detections. So now I will discuss the impact of this system. So for me, this project helped me understand visible light communication and OOK modulation more clearly, and then learn how binary code can be transmitted using LED light, and how a receiver can recover the data through threshold detections. And it also helped me connect communication theorem with the practical emergency applications. So for the community, this system could provide faster local emergency warnings, so it can be used for road closure, flood warning, and evacuation alerts. So since it reduces LED streetlights, it may reduce the need for complete new communication infrastructure. And it can also act as a complementary warning method when cellular networks are congested or unavailable. So for the country, this system supports a smart city and smart rural development. So it can improve emergency management infrastructures and provide a low-cost additional public safety communication method. So the main impact is that the existing public lights can be upgraded into an additional emergency communication network. So in conclusion, the proposed systems use LED streetlights to transmit emergency alert, and OOK modulation send the alert as binary light pulses. And for the diode receivers recover and decode the message, and the message shows that distance, ambient light, and alignment affect communication reliability. So overall, VOC can reuse existing LED streetlight as an additional emergency warning system for roads and public areas. So that is all for my presentation. Thank you for listening.